Okay, let me first give you the answer to the break exercise, which basically asks you to rewrite the Freeman equation uh, as the expression for Hubble's constant and the deceleration center, the time dependences, of course, in terms of the time dependence of the density and scale factor. Uh, so the first equation asks you to rewrite the first Freeman equation as a t-dependent Hubble's constant. It was a Hubble constant related to Hubble constant at now to this factor which depends on the density. Okay. Remember that we written down two expressions for the Freeman equation. This first one I wrote down. Then I rewrote and I structured the first Freeman can be written another way. Okay. These are two equivalent expressions of the first Freeman equation. Now you substitute the curvature term, k term here by the second expression. Okay. So therefore, a dot a square term is equal to the term keep the same as the right hand side, a pi Newton constant 3 times density. Then this term here is now it's the same as this except divided by a square. So this just this expression here divided by a square. Okay. Now a dot a is h, so therefore this h squared is equal to uh, this term here. Now this term a pi g over 3 is h naught squared divided by the critical density. So I factor out this h naught both term here, and then I have left with the density divided by critical density, which eventually we can written as density parameter. But anyway, it's density over critical density, and this term just factor h naught. There's still a squared term here. So that's the expression we're looking for. So it's just straightforward substitution. Okay. Now, the second Freeman equation can be written as a time-dependent expression for the deceleration parameter, okay, which is defined this way. Okay. Now, remember the fact the equation state parameter W is a pressure in units energy density. So the second Freeman equation, which here can be rewritten as just divide by minus 1 over h squared on both sides. So I have a minus a double dot over ah on the left hand side. Here take out the minus sign, 4 pi just h squared. Now I'm going to factor out this 1/3 of rho c squared density. So the last second just 1, but the first term because I have h over that's the w, so I have a factor 3w. Okay, and then you just the left hand side is just the definition of the acceleration parameter, and the on the on the right hand side is the same factor, and this multiplied by 2 divided by 2. This is the c squared cancel, so you'll have uh, the density over the critical density, so that's omega, and so this is this is the expression we're looking for. These expressions for h and the q are very useful later on. We're going to decide whether the universe expansion is accelerating or decelerating, and also to find out how the rate expansion in terms of density. Okay, on to the second part of the lecture 23, so-called Newtonian interpretation of Freeman equation. Although Freeman equations are part of the Einstein GR equations, actually these Freeman equations have rather simple Newtonian interpretations. Okay. So the question is whether Newtonian interpretation is applicable here. previously we argued that GR must be the proper framework to study cosmology. Indeed, the Freeman equations determine the scale factor and the curvature, which are fundamental parameters of a curved space-time description. Nevertheless, these equations have rather simple Newtonian interpretations when supplemented by global geometric concepts. Okay, so if you, of course, with Newtonian interpretation, it's much easier for most of us to understand the meaning of these equations. There's no contradiction to say it's GI equation, yet at the same time have Newtonian interpretation. Because the cosmological principle states that every part of the universe, large or small, behave the same way. So when we concentrate on a small region, a Newtonian description should be valid because the gravity involved is not strong and the small space can always be processed by a flat geometry. Okay. So therefore, it is possible to understand the cosmological equation with a Newtonian approach when carried out in the overall framework of GR, overall geometric framework. But remember when we discussing the homogeneous isotropic universe, we ignore any peculiar motion of galaxies relative to the cosmic fluid. That's any change galaxies co-moving coordinates. Okay, so the only dynamic effect we'll be interested in is the separation us by the scale factor. Okay. So therefore, the only relevant dynamic question is the time dependence of separation between two fluid elements, and we call this the Hubble flow. So let's consider a fluid element with mass m, okay, which is element. Remember, a fluid element composed a collection of galaxies. In the cosmic fluid, and we arbitrarily pick an origin, O. Okay, the distance from the fluid element to the origin is given by r, and of course it scales like a times some constant r naught, or co-moving. And also we have spherical symmetry respect to the origin O, because homogeneous isotropic space is symmetric with respect to every point. So therefore, suddenly to the point we pick O. So we should study the effect of gravitational attraction on this this element M by the whole fluid, which is spherical symmetric with respect to O. So therefore, the gravitational attraction due to all the mass outside this Gaussian sphere, radius r, is get cancelled. They mutually cancel. This is a familiar known relativity effect, but it's also valid to know in GR, which is part of the so-called Birkhoff theorem we talked about in lecture 14. So M feels only the total mass M inside the sphere. Okay. And also, this is a particular simple central force problem because, remember we talked central force problem from talking about Mercury orbit in lecture 15. There's only radial motions, the Hubble flow, that's zero orbiting angle, so we don't have to worry about the orbiting angle, so we just cross out a term. So it's just really a two term on the left hand side. So this energy balance equation, kinetic energy by the radial motion and the potential energy equal to total energy. Okay. Now we substitute here. We have substitute to r equal to uh, a r naught. So the v squared is equal to a dot r naught. So the total mass inside, we can talk before small area, we can have flat geometry, is mass times density times the expression for a sphere in the uh, in, in a flat space. So therefore, divide out by m over 2 r naught square. So the first term is a dot square, and the second term here, okay, just work out to be a pi 3 rho a square. Just substitute m into here. And you also add m for r squared, the r naught squared that's divided out by this. So the left is divided by 2 over multiplied divided by m over 2r naught squared. Now divide by a squared, and we have this expression here, this a squared. Now compare this the first Freeman equation. Okay, so this term are exactly the same. The only difference on the right hand side term. Okay, so therefore, if we identify the right hand side term, then we can interpret that's the first Freeman equation. Simply is the energy balance equation in the Newtonian interpretation. Okay. Now, to justify the identification of the right hand side, remember we calculate with arbitrary origin. Different choices we have different value R naught and different total energy, the E over M. So the assumption of homogeneous isotropic space led GR to conclude the right hand side is a constant with respect to any choice of O. Okay. So anyway, the first three can be interpreted as simply the energy balance equation. But with the total energy is identified somehow with the curvature signature term. So the Newtonian interpretation of Freeman equation, as I said, the first one can be thought as the energy balance equation, and I'll leave it as an exercise for to show the second Freeman equation is just F equal to ma equation. So the important point is now can relate the curvature to the total energy. Okay. As we shall see, we actually live in a flat universe, which means k equals 0. Thus, we are in the universe we live in actually has a remarkable simplicity with a total zero energy. Okay. So it was the kinetic energy expansion and the gravitational attraction is precisely cancelled. Okay. That's really amazing and simple. And also we can make a comment, the mass density is actually determined by the fate of the universe. And we're going to argue the critical density behaves something like a escape velocity. Remember, in a central force problem, whether the motion is of a test mass is bounded or not, determine the sign of the total energy. Okay. Right, because if the total energy is positive, means that the particle can go to infinity. When it goes into the potential energy vanishes, so this term must be positive. So if the particle is able to escape to infinity, the total energy must be positive. And same way, if it's bounded, the total energy must be negative. Okay, so therefore the energy balance, whether it's positive or negative, of course, is determined by whether the kinetic energy is bigger than the potential energy or vice versa. So remember our definition, our introduction of escape velocity. So we want to compare kinetic energy to a given potential. If suppose the potential energy is given, you ask what kind of kinetic energy can, whether it's bigger or smaller than the potential energy in order to see whether the system is bounded or unbounded. So to do this, we rewrite the potential energy term as in the form like kinetic energy, except the velocity is defined, of course, this way in order to have this relation. So the escape velocity is 2g m over r square root. Now, once you use this definition, I can factor out this potential energy term on both sides. Then you get v squared over v over v escape velocity squared minus 1. So you can easily see if v is greater than escape velocity, then the total energy is positive, so the particle can escape to infinity. Now we can do another way. And we suppose the kinetic energy is known. Okay, you ask what kind of potential energy the size would be in order to whether the system is bound or unbound. So the same trick. We're now, since the kinetic energy is known, so we rewrite the kinetic energy in the form of a potential energy term and define a critical mass. The critical mass, according to this formula, is is small m cancel this r over v squared and 2g in the denominator. So therefore, this energy balance equation can be written away, and you can see that m is greater than critical mass, then this is negative, so the total energy is negative, it's bounded. If m is less than the critical mass, it's unbounded. So it's not enough mass to hold it. So this analogous question in cosmology, whether given an expansion rate, which means given the kinetic energy, you can ask whether test galaxy M is or fluid element is bound by gravitational attraction of the cosmic fluid. Is determined by whether there's enough mass in the arbitrary sphere on the surface where M resides to prevent M from escaping completely. Name the value of K as minus the total energy determines whether this universe not only determines the geometry, but also determines whether the universe will expand forever or expansion will eventually slow down and will collapse. Now, since the sphere is arbitrary, what matters is not the total critical mass, rather the density of the cosmic fluid. So you divide the critical mass by the volume to get a density. And remember, r is a r naught, v is the velocity is a dot r naught. So so the critical mass divided by volume, critical mass you have 3 power distance, so you have r cubed a dot because the velocity is a dot, and over 2g, that's the critical mass. And the volume is just Euclidean space volume for a sphere, 4 pi r cubed over 3. Okay, now cancel r, cancel 1 to the power a, and so therefore this a dot squared a squared, so that's h. So you find this expression is precisely the critical density we've been talking about. Okay. So therefore, the critical density plays same kind of role as a more familiar escape velocity. Uh, One is, of course, given potential energy and find what kind of velocity can allow particles to escape. Here is, if given the kinetic energy, what kind of mass can hold it into a bound system. Okay, that's the end of the second part of lecture 23.